Well, hello again. I'm going to talk about rotational energy and angular momentum. So first, rotational kinetic energy. So last time we saw that torque equals I alpha. So this was like F equals ma for something translating through space. By translating, we mean moving through space. And now we were talking about, rather than something moving through space like that, we were talking about some, say, solid object that would be rotating, and this relates a torque to an angular acceleration if it's speeding up. And this I was the moment of inertia, the rotational inertia. It depends on how much mass the object has and where that mass is. So for example, for a ring of radius r, all of the mass, if it's mass m and radius r, the moment of inertia is mr squared. Whereas for a disk of radius r, where the moment of inertia is 1/2 mr squared, so they have the same mass, but it's distributed differently. So here, all of the mass is at some large distance from the axis. The dashed line is the axis. Here, some of the mass is near the axis and some is far from the axis. So the mass that's far from the axis contributes a lot to the moment of inertia, and the mass that's near contributes only a little bit. So this has a smaller moment of inertia than this does. But this moment of inertia is a measure of resistance to rotational acceleration. So just a reminder of what we learned last time, and we saw that torque was this moment of inertia times alpha. So just as we have this analogy here, we have analogies for energy. So kinetic energy of something moving through space with some mass m, looks like 1/2 mv squared. And this is called kinetic energy of translation, translational kinetic energy now. There's also a rotational kinetic energy if something is rotating. Suppose it's spinning with some omega, and that looks like 1/2, instead of m, there's now I, instead of v, there's now omega. So rotational kinetic energy is 1/2 I omega squared, and what we use for I is different than just the mass. We have to use whatever the moment of inertia of that particular shape is. If it's this thing spinning, we use this. If it's this thing spinning, we use this. If it's a sphere, for example, it's kind of a hard time drawing a sphere. I is 2/5 mr squared. By the way, I would give you a table of moments of inertia on a quiz. I don't expect you to memorize these. And so whatever the I is, then 1/2 I omega squared is the kinetic energy of a rotating or spinning object. So if something's doing both, like if we have a disk rolling down a ramp, so rolling down a ramp, now that disk has a V and an omega, so its kinetic energy would be 1/2 mv squared plus 1/2 I omega squared. Its kinetic energy would be its translational kinetic energy plus its rotational kinetic energy. You have to account for both, because it's got energy because it's moving through space, translational kinetic energy, and energy because it's spinning, it's rotating. And notice when it starts at the top of the ramp, it has gravitational potential energy as well. So it's only writing the kinetic energy there. So let me just do an example, just calculating just an energy like this, a rotational energy of the Earth. So the Earth is a sphere, so its moment of inertia, if we look it up in a table, is 2/5 mr squared. So I looked up the mass of the Earth and the radius of the Earth. So this is 2/5. The mass of the Earth is 5.97 times 10 to the 24 kilograms. The radius of the Earth is 6.371 times 10 to the 6 meters squared, because this radius is squared. And this gives me 9.696 times 10 to the 37 kilogram meter squared. The Earth has a large moment of inertia. It takes a lot of effort to rotate the Earth. Notice the unit is just kilogram meter squared. There's no special name for that, for the unit of moment of inertia. We need omega. Omega for the Earth is 1 revolution every day times a day per 24 hours times an hour per 3,600 seconds times 2 pi radians per revolution, and that turns out to be 7.27 times 10 to the minus 5 radians per second. So now we know I, we know omega, so kinetic energy of rotation of our planet is 1/2 I omega squared is 1/2. I was this 9.696 times 10 to the 37 kilogram meter squared. Omega is this 7.27 times 10 to the minus 5 radians per second squared, that quantity squared. This turns out to be quite a large number, 2.56 times 10 to the 29 joules. So quite a lot of energy. All right. So that's our introduction to energy. And if we were doing conservation of energy, all we would now need to do is add in the rotational energy anywhere that it appeared. Next topic will be rotational momentum, but it doesn't go by that name. It goes by angular momentum most of the time, maybe even all the time. And there is a law of conservation of angular momentum. So first, angular momentum. So remember what momentum was. Momentum P was defined to be mass times velocity. So continuing our analogy, so to go to rotational quantities, angular momentum is given the symbol L. I don't know why it's given the symbol L, but it is instead of mass, what do we use? We use moment of inertia. Instead of velocity, we use angular velocity omega. So angular momentum is I omega. So again, for the Earth rotates on its axis and has some omega. We just computed these numbers. I erased them, but you should, you can either go back in the video or if you're taking notes, have them in your notes. That I, 2/5 mr squared of the Earth, was 9.696 times 10 to the 37 kilogram meter squared. Omega of the Earth was 7.27 times 10 to the minus 5 radians per second. So now the angular momentum of the Earth is just I omega. That's the product of these two numbers. I'm not going to write them again. Is 7.05 times 10 to the 35. Your book uses the units kilogram meter squared per second. That's fine units, that works. Moment of inertia, I, is units kilogram meter squared. Omega is radians per second. But remember, a radian's a meter per meter, so we can just erase that. This is actually equal to a joule times a second. I won't prove that right now unless you ask me to, but you can't because this is a video. But so often you'll see this expressed as a units of joule times second. And that's the unit I use. A kilogram meter squared per second is of course correct as well. So that's our definition of angular momentum. That's this rotational momentum something has. Now, there is a law of conservation of angular momentum. Remember, there was a law of conservation of momentum. That law said if the net external force is 0, then momentum before an interaction equals the momentum after. So there's a law of conservation of angular momentum. It's really very important that many things in nature can be explained from this law, like how hurricanes behave, how the shape of disks in galaxies. Anyway, the law of conservation of angular momentum says if the net external torque is 0, so there is this constraint, if there's no external torque, then the angular momentum before an interaction equals the angular momentum after. So when something is unchanged in physics, we say it's conserved. When energy is not changing, we say the energy is conserved. When momentum is not changing, we say momentum is conserved. When angular momentum is not changing, we say angular momentum is conserved. That's how we use the word conserved in physics. So this would say that if you add up all of the, remember angular momentum is I times omega, add up all of the I omegas before, then you get the same answer as if you add up all of the I omegas after whatever interaction you're talking about. Most of the time those interactions are some sort of collision between two objects. So I'm going to do an example of that for you. So here's the example I've come up with. I've got a merry-go-round that's a simple disc spinning on its axis. So this is a merry-go-round. It has a radius of 2 meters, so it's a little merry-go-round. It has a mass of the merry-go-round of 200 kilograms. And it's spinning at, the merry-go-round is spinning at, let's see, 60 RPM, revolutions per minute. And out here at the very edge, we're going to drop a tiger on the merry-go-round. We're going to just drop it onto the merry-go-round. So when you drop an object on the merry-go-round, I think you know from experience, it's going to slow down. Because the angular momentum before is going to equal angular momentum after, and there's going to be an increased moment of inertia. And adding the tiger to the merry-go-round will increase the moment of inertia. This is supposed to be a tiger. Okay. So before the tiger hits the merry-go-round, we've got I of the merry-go-round, omega of the merry-go-round. Afterwards, we've got I of the merry-go-round plus, we've now dropped the tiger on it, I of the tiger. Get it? I of the tiger times omega final. So what we want to know is omega final. So omega final is just I of the merry-go-round before over I of the merry-go-round plus I of the tiger, I of the tiger times omega of the merry-go-round. All right, well, I of the merry-go-round is I of a disk, and I of a disk is just 1/2 mr squared. That's 1/2 the mass of the merry-go-round, 200 kilograms, times its radius, 2 meters squared. Half of 200 is 100 times that, so that's 400 kilogram meters squared. I of the tiger, well, we got to know the mass of the tiger. The mass of the tiger, what did I pick? I picked the mass of the tiger to be 50 kilograms, so it's not a very big tiger. It's out here at the full radius, and so I'm treating it as a particle, as if I've just dropped like a glob of something on it. And for a single particle, I of a particle at some radius is just given by mr squared. That's I of a particle. So for I of the tiger, it's just the mass of the tiger, 50 kilograms, times the radius, 2 meters squared, because that's where the tiger is, out here at the very edge of the merry-go-round. And 50 times 2 squared is 200 kilogram meter squared. Omega is 60 revolutions per minute. So let's see, let's do this first. I've got I of the merry-go-round is, where is that? 400 kilogram meters squared over 400 kilogram meters squared plus 200 kilogram meters squared times omega, the merry-go-round. Now I could convert omega to radians per second, and this would give me radians per second here. Or if I just, since this is just multiplying, if I just leave it in RPM, I'll get RPM here. So if I just leave it in RPM, this is times, well, maybe I better do it in radians per second, just so you're accustomed to it. Omega to rate in 60 RPM is, if I do the conversion, it's 6.28 radians per second. So times 6.28 radians per second. So I did the conversion already for you. So omega final is this. That gives me 4.19 radians per second, which is just 40 RPM, which is what I would have gotten if I just put 60 there, multiplied by these things. So sure enough, it was going 60 RPM. We dropped the tiger on it. It slows down to 40 RPM from conservation of angular momentum. All right, so I will see some of you in class on Friday, and we'll look at rotational energy and angular momentum there. And you can practice it in your homework as always.